Hi everyone, welcome. This is going to be the review session for Math 110 College Algebra for our second exam in the class. The first topic we're going to look at is example 1, where we have to evaluate a function at some indicated values. Here the function is f of x equals x squared minus 8x plus 3. Again, it's helpful if you can think of the statement form of a function. This function f of x is designed such that what it's supposed to do, it's going to take our input, square it, subtract 8 times the input, and then it's going to add 3 to it. So for instance, if we wanted to evaluate the function at negative 3, then everywhere we had an x, we're going to replace it with the number negative 3, like this, and then we'll simply follow order of operations to get the value. Exponents first, we're going to get 9 minus 8 times negative 3 plus 3. Next thing we would do would be to multiply. Negative 8 and negative 3 will make a positive 24. And then we can go ahead and add. 9 plus 24 is 33, and 33 plus 3 should give us 36. So f of negative 3 is equal to 36. For the next part, we want to find f of negative x. So once again, wherever we had x in the original expression, we need to replace it with negative x. After we do the substitution, let's simplify any of the signs that we can. Negative x squared means negative x times negative x, which is the same thing as positive x squared. Negative 8 times a negative x is a positive 8x, and then we have plus 3. So this would be the expression for f of negative x. The last evaluation we want to do with this function is we want to find f of t minus 4. So everywhere we had an x, we're now replacing it with the input t minus 4. So let's go ahead and plug that in. T minus 4, t minus 4 like this. From here we want to simplify it, and let's pay close attention to this step right here. Okay. When we have something like the expression t minus 4 squared, that's a binomial squared. That means to do t minus 4 times t minus 4. And to do that, we have to use the distributive property. Some of you might also recognize this as being FOIL. T times t is t squared. T times negative 4 is a negative 4t. Negative 4 times t is a negative 4t. And negative 4 times negative 4 would give us positive 16. We can combine those two middle terms, and what that will yield will be the following. We have t squared, negative 4t and negative 4t combined to give negative 8t plus 16. For the next term, we can distribute the negative 8 into that parenthesis. That will yield a negative 8t plus 32 plus 3. And then the last thing we can do is just simplify our like terms here. We have a t squared term, which is this one right here. Our t terms are these two. We have a negative 8t and another negative 8t. We'll make negative 16t. And then 16 plus 32 is 48, plus another 3 would be 51. So f evaluated at t minus 4 produces t squared minus 16t plus 51. The next thing we come to is evaluations, but with piecewise defined functions. Recall that for each input you have into a piecewise defined function, the particular piece it will get plugged into is dependent upon which of the test conditions it satisfies. And whenever we have a true piecewise defined function, each input x will always satisfy at most one of these test conditions. So you don't have to worry about plugging it into more than one expression. Each one will only get plugged into one spot. For example, if we want to find the value f of 8, when x equals to 8, that is going to be a value that is greater than or equal to 2. So that input satisfies this test condition, which means we would plug it into this piece here. it's going to be the square root of 8 plus 1, which is the square root of 9, which would give us the value 3. For the next value, f of -3, -3 is not less than itself, but it is greater than or equal to itself. So this one's going to get plugged into the second part, the x squared minus 5 piece. So we get -3 squared minus 5. That's going to be positive 9 minus 5, which should give us the value 4. For an input of -5, notice that -5 is less than -3. So that means we're going to plug it into the top part. So it's going to be -5 plus 1, which would give us an output of -4. And then lastly, to find the value for f of 2, 2 is greater than or equal to itself. So it's going to get plugged into this bottom one. This is going to be the square root of 2 plus 1, which is the value square root of 3. So that's evaluation with piecewise defined functions. The next topic we come to is the domain of a function. And at least at this part right now in our class, whenever we're finding the domain, so recall what the domain is. It's the collection of x values that we can plug into the function such that we actually get an output out of the function. Typically, to ask what kind of things we're able to plug in, we turn around and ask the converse and say, well, what things can't we do? And for right now, the two big restrictions we have is we cannot divide by 0. So if you have a fraction with any denominator, you need to set that denominator not equal to 0. The other major restriction we have is whenever we have an even root. So things like square roots, fourth roots, sixth roots, etc. To get a real value out of this, the part that's underneath the radical has to be greater than or equal to 0. So for right now, those are the two major restrictions we have as it pertains to domains and function evaluations. If we look for the domain of the function in part A, this is f. So the domain of f, notice that it's a polynomial. It's 5x squared plus 2x minus 1, which is really just a combination of exponents, multiplications, additions, and subtractions. And those operations you can always do with any two real numbers. Another way to think of it is there's no fractions, there's no radicals, so there's no problem with this one. It will have domain all real numbers, i.e. it'll be the set from -infinity to +infinity. And technically speaking, whenever we write domains and ranges, it's always best to give them as intervals, because that's the proper way to do it. If you write R, the set notation for real numbers, or if you say all reals, I'll also accept that too. That's perfectly fine. Let's take a look at the function g now. G of x does have some denominators with some variables in it, so we can't divide by 0, so we need to make sure that neither one of those denominators equals to 0. If I set the first one equal to 0, that would say that x is equal to 0. So that's going to be a restricted value. X cannot be 0. For the second denominator, if I set it equal to 0 and solve, we would get x equals to -2. So that would be the second restriction that we would have here. So for g of x, every real number, with the exception of x equals to 0 and x equals to -2, will be in the domain. Again, for shorthand notation, if somebody wrote this for the domain, I would accept it. But it is best to put these in interval notation. What does the set of real numbers, excluding 0 and -2, look like? Well, if you look at the graph of this thing, here's the number line, here's 0, here's -2, and recall that these are the two values that we don't have. So those are not included. We know that that means that those would be open circles. But every other part of the real line would be included. So everything else would be good for us and is in the domain of G. And so it's going to be this set here. And if you have the graphed interval, I find a lot of times that helps students to be able to write an interval notation. It's kind of 3 disjoint intervals. we have the part from negative infinity up to but not including negative 2. Then we have the part between negative 2 and 0, not including those. Union. Then we have the last interval, which is everything not including 0 and all the way towards positive infinity. So this would be the domain for G. Our last function, h of x, we do have a square root. For the domain of this, we require the thing on the inside, which is the expression x plus 6, has to be greater than or equal to 0. To get the x by itself, simply subtract 6 from both sides, and we get that x is greater than or equal to negative 6. If it helps, you can graph this first before doing the interval notation, but the set of x is greater than or equal to negative 6 would be everything from negative 6 included all the way towards positive infinity, and that would be the domain of h. Let's take a look at another one here. In example 4, we want to find the domain of each function. The next one is j of x, and this is the fifth root of 2x minus 8. Now, on one hand, yes, we do have a radical, but this is an even root. Remember, you can take even roots of any real number. For example, if I had a cube root, like I could have the number negative 8 inside, and the cube root of negative 8 would simply be equal to negative 2. So odd roots don't pose us any problems. I look inside the function, and we just have the nice polynomial 2x minus 8. That will always produce some real number, and whatever number we get, we certainly will be able to take the fifth root of it. So j of x is not going to have any restrictions or any problems here. The domain of the function j is going to be equal to all real numbers. So from negative infinity to positive infinity. We have one more. We have the function k of x. Notice that there's two things that are going on with k. So first of all, we do have a denominator with a variable x in it. So one restriction is we cannot let that denominator be equal to 0. The second thing that we have going on here is we have an even root. So we also require for the part on the inside to be greater than or equal to 0. We're now going to solve each of these expressions individually. For the first one, to get the x by itself, we can just square both sides. This would say that x minus 10 equals to 0. We add 10 to both sides, and we get that x equals to 10. Now that value, x equals to 10, that's a number that would make the denominator equal to 0, and so that will not be in the domain of this function. Over here, to solve this inequality, we can add 10 to both sides. So add 10, add 10. This would produce x is greater than or equal to positive 10. And for the domain of this function, we need for both of these conditions to be satisfied. So we need simultaneously for x to not be equal to 10 and for x to be greater than or equal to 10. And those two conditions you can combine as one condition. It's x has to be strictly greater than 10. Okay. So again, for the square root portion of it, you can take the square root of 0 and get a real number. So if x equals to 10, that gives us the square root of 0, which is 0. That's not an issue with the square root portion of the function, but the issue then becomes is that 0 then immediately ends up in the denominator, and we know that we cannot divide by 0. So again, the domain of this thing, it's all x is strictly bigger than 10, which would be from 10 not included up to positive infinity. In the next examples, we're going to work with the difference quotient, f of x plus h minus f of x divided by h. Please commit this formula to memory. It's a very, very important formula in mathematics. And in many ways, it's the basis for calculus. You'll see that later on in future classes. We talked about this. What it represents is a couple different things. You can think of it as the average rate of change of the function f over the interval x to x plus h. It also represents the slope of the secant line of f, again, between x equals to itself to x equals to h, x plus h. Let's go ahead and find this difference quotient. In the lectures, I kind of highlighted a good strategy for doing this. And whenever you're dealt with a difference quotient, what you want to do is kind of break it apart into three pieces. In the numerator, we have two function evaluations, and in the denominator, we always have h. So h always immediately goes in the denominator. The expression that's getting subtracted is always the original function. That's going to be negative 5x plus 1. And again, I use the brackets here for a couple of different reasons. Not only does it visually help us to determine the key pieces that we're working with here, but the other thing, it's absolutely important and essential for this one, because when you're subtracting f of x, like we are in the difference quotient, if f of x has multiple terms, we need to make sure that we're subtracting every single term that belongs to f of x. And then this piece here, this is the one that often requires a little bit of work. Let's do that off to the side. Let's find f of x plus h. So I'm going to recopy the original function, but I'm going to use a parenthesis as a placeholder for my variable. Everywhere we had an x, an expression for f, we're going to evaluate it at x plus h, and it looks like this. Let's now go ahead and simplify this by distributing. This would give us negative 5x minus 5h plus 1. And so that's our work for f of x plus h. We can now go ahead and plug that in. And now our goal is to simplify this. In the numerator, we can distribute the negative sign through. So we have negative 5x minus 5h plus 1. This will now become a plus 5x and a minus 1, all divided by h. After doing so, we have some like terms that are going to cancel here. The negative 5x and the positive 5x cancel. A positive 1 and a negative 1 cancel. And what we're left with right now is we have a negative 5h divided by h. And now it turns out that the h's cancel from top and bottom because they're common factors. And we're left with the answer negative 5. So the difference quotient for this function simplifies to negative 5. And if you recall, this is one of the tips that I gave us. Whenever you're working with a difference quotient, you will know that you have it simplified all the way if eventually towards the end of the problem, if you get the original h that was in the expression, should somehow be able to cancel out. Let's take a look at number 6. Again, we want to find and simplify the difference quotient for this new function, f of x equals x squared minus 5x plus 8. Again, get into good habits. We're going to have f of x plus h minus f of x, and that's all going to go over h. So we put h in the bottom. We know we're subtracting f of x, that is x squared minus 5x plus 8. And once again, a lot of the work of this problem is let's find that f of x plus h somewhere here off to the side. So our function was x squared minus 5x plus 8. X squared minus 5x plus 8. Everywhere we saw the variable x, we're going to replace it with an x plus h. And now from here, we just need to simplify this. This first term, as we saw previously, this is the square of a binomial, so we have to distribute that out. X times x is x squared. X times h is xh. H times x gives us another xh term. And then h times h would be h squared. Distributing the negative 5 into this parenthesis, we get a negative 5x, a negative 5h, and then don't forget we still have that plus 8 tagging along. The only other thing we can do with this step is we do have some like terms here we can combine. This gives us 2xh plus h squared minus 5x minus 5h plus 8, and that is our simplified version of f of x plus h. So let's go ahead and plug that into our difference quotient. X squared plus 2xh plus h squared minus 5x minus 5h plus 8. It's all set up for us. Now it's time to go ahead and to simplify this. And to do that, we have our first term, x squared plus 2xh plus h squared minus 5x minus 5h plus 8, and we're going to distribute the negative sign in. Negative x squared, positive 5x minus 8, all divided by h. Let's see what cancels here. A positive x squared and a negative x squared cancel. We have a negative 5x and a positive 5x cancel. And we also have a positive 8 and a negative 8 which cancel. That leaves us with 2xh plus h squared minus 5h all divided by h. Now at this step, there are no more like terms to combine, but if we look at the numerator, all of those terms have a common factor of h. And that means it's a GCF, so we can factor it out. If we factor an h out from the numerator, we're left with 2x plus h minus 5. And then here the h's cancel, and we get our final answer, 2x plus h minus 5. So 2x plus h minus 5. In the next question, we have the graphs of some expressions, and we want to know whether or not these graphs represent that of a function or not. Okay. So let's take a look at the first one. The graphical method, the tool that we have for this, was called the vertical line test. Clearly, you can find some vertical lines that will intersect this graph in more than one point. So the conclusion would be no, this graph is not that of a function. Not only do we say that it's not a function, but we also want to kind of give our reasoning. And so make sure you quote the vertical line test. So it's not a function, and our reasoning is by the vertical line test, which you can abbreviate VLT. If we look at the graph in part B, we see that no matter what type of vertical line we draw, it will only ever intersect the graph in at most one point. And so the graph in B is a function. And again, our reasoning is by the vertical line test. The next question we're going to look at is to find some information based upon the graph of a function. Whenever you're looking for the domain of a function, remember, those are the collection of x values. So you're essentially asking the question, how far to the left to how far to the right does the graph go? This graph, the leftmost point is this one right here, which is at x equals to 0. It goes as far to the right as this point, which is at x equals to 5, but notice that that's an open circle. So that point is not included, but we would have an x value anywhere in between those two. So the domain, again, coming from the x-axis, this is going to be equal to the set 0 included up to, but not including 5. The next part wants us to find the range of this function. So let's do that. So we want to find the range of f. When it comes to the range, now we're looking on the y-axis. So you want to identify the lowest point, which is right here. That's at y equals to -1. the highest point, it goes up to 5, but it's not included. And then we're able to hit every single height in between -1 and 5. So the range of this function is going to be the set -1 included up to, but not including 5. The next thing we want is the X-Intercept. Keep in mind that technically speaking, intercepts are points. So we want to find where does this graph intersect the x-axis, and it happens right here. So this is our x-axis. This graph crosses the x-axis at this point, which is the order pair 2, 0. We also now want the y-intercept. So we want to figure out where does the graph cross the y-axis. That's right here. That's the point 0, -1. The last thing they ask is for the value of f at 0. So the way that we work this, to find the value of a function from its graph, we go on the x-axis, x equals 0 is here. You then trace either up or down to locate where the point is at. The point is right here. And that corresponding y value is -1. Remember, on a graph, the order pairs can be written as x, f of x. So if you want the value for f evaluated when x is equal to 0, it's just the y value of that point. So f of 0 equals to -1. And we actually have one more portion of this. We want to find the x values for which f of x equals to 3. So here we're looking to get an output of 3. So it's kind of like a reverse lookup, if you will. So if f is equal to 3, that would correspond to a y value of 3. And I'm just going to draw this horizontal line. These are all of the heights when y is equal to 3. That would intercept the curve at this point right here. And notice that that happens for the x value 4. So f of 4 equals to +3. So for which value of x does x equal to 3? We found it's x equals to 4. Let's take a look at the next graph. Here we want to find, first of all, the domain and the range. Again, for the domain, you're looking on the x-axis, how far left to how far right. Notice because of the presence of these arrows, this indicates that this graph will continue to go down and to the left forever. It'll also continue to go down and to the right forever. And there's no gaps or no breaks, so we hit every single x value here. So the domain of this function would be all real numbers, from -infinity to +infinity. For the range, we want to look for the lowest point to the highest point. Notice again, because of the presence of these arrows, this is going to go down and down and down and down forever. So the range will approach -infinity. But there is a highest most point. The highest point on this graph is here, and that corresponds to a y value of 4. And you can very easily see that we are able to accomplish and achieve any y value from -infinity up to 4 included. So that's set on the y-axis. The range is from -infinity up to 4 included. The next question asks on what intervals is the function increasing. Typically, whenever we do increasing or decreasing, you want to read the function like you would a book. And remember, these are intervals on the x-axis in the domain. When we start out from -infinity, as we go to the right, notice that the graph is going up and up and up and up. And it continues to go up until we get to this point here, which is at x equals to -2. So from -infinity to -2, the function is going up. And recall, with increasing and decreasing, we don't consider these endpoints to be either included. They're always kind of excluded because those are the points where you might have a change in behavior. Now, but for the next little bit, it's going to decrease, decrease, decrease. Let's kind of categorize that. The graph decreases from -2 up until we get to this point here, which is at 0. So from -2 to 0, the graph is decreasing. So increasing here, decreasing here. Let's go ahead and summarize that. From -2 to 0, it's decreasing. Again, on the x-axis, if we continue to move to the right, now the graph is going up and up and up until we hit x equals to 3. So between 0 and 3, it's going up or increasing. So union 0 to 3, increasing. And then once we move beyond x equals to 3, this thing's going to continue then to decrease forever. So it's going to decrease from 3 to positive infinity. They also ask on what intervals is the function constant, and the answer is none, right? To have a function that's constant for a little bit, what that would look like is there'd be an interval where the graph of it would be horizontal, right? So for example, if I have between A and B here, that would be an interval where this graph would be constant. Okay. But there's no kind of like horizontal spots, if you will. They want two more things. They want the relative maximums and relative minimums. Remember, these correspond to locally low points or locally high points. So kind of like peaks or valleys. The relative extrema, there's going to be one here, as well as one here. The first point we see, this is going to be a relative maximum. And the relative maximum value is always the function value. So we have a relative max of 4 at x equals to -2. So relative max of 4, and it occurs when x equals -2. This point here is a relative minimum, and it has a value of function value of 1. So we have a relative min of 1, and that occurs at x equals to 0. And then the last relative extreme we have is this value here, which is a relative maximum. The relative maximum value is 2, and this occurs when x equals to 3. So relative max of 2 at x equals to 3. Let's take a look at another example. In example 10, we want to find the domain of this function. Let's just call this function for argument. Let's just call it g of x. If we look for the domain, notice the presence of these arrows. This graph goes all the way to the left. It goes all the way to the right. There's no jumps or breaks in the graph, so we're going to have every x value between -infinity to positive infinity. So the domain of this function is all real numbers. When we look at the range, this graph does have a lowest point, or lowest points in this case. The lowest on the y-axis this graph will ever go is the y value of 0. And again, because of the presence of the arrows, this graph will shoot up and up and up and up forever. So the range of g is going to be equal to 0 to infinity. The next question is on which intervals is the function increasing? So let's do increasing, decreasing, and constant all in one swoop. So when we start off by reading the graph from left to right, as we would a book, initially we see that the graph is going down and down and down, and it continues to go down up until we hit x equals to -3. So this graph is decreasing from -infinity to -3. So let's plug that in. So they don't actually ask for it. Let me change part D to decreasing. So from -infinity to -3, the graph is decreasing. Now what happens next? From -3 on, it starts to go up and up and up, and it continues to go up until we hit to this point, and that appears when x equals to 0. So between -3 and 0, the function is increasing. Between 0 and it continues to decrease until we hit x equals to 3. So in this interval, it's decreasing between 0 and 3. And then from 3 and onward, the graph will continue to increase. So it increases from 3 to infinity. Notice the original part D had asked about constant. This graph is constant nowhere. There's no places where this graph is horizontally oriented. We now want to look for relative minima. Let's do both relative min and relative max. There is a couple relative extrema. There's one here, and one here. This point here happens to be a low value, so that's a relative min. The y value is 0, so we have a relative minimum of 0, and this occurs at x equals to -3. This value here, which is 4, is a relative max, and that occurs when x equals to 0. And this is a second relative minimum. This is a relative minimum of 0, and that occurs when x equals to +3. So at x equals to +3. Part G asks, is the function even, odd, or neither? And this one is actually going to be an even function, and the explanation is because it has a y-axis symmetry. So if we go back up to the top, if we were to take and draw a line on the y-axis, and imagine if this was like a piece of paper, and if you were to take and crease the paper along the y-axis and fold it, what you would see is that when you fold it, the graph would perfectly match up. That means that this graph has a y-axis symmetry, which means that it's an even function. So y-axis symmetry is indicative of even functions. We had another type of symmetry, which was an origin symmetry. And if a graph had an origin symmetry, then it was an odd function. Okay. The best examples to think of origin symmetries, you can think of them as double reflections about both the y and the x-axis. But to kind of see an example, x cubed is a classic example of a function that has an origin symmetry. Or even like the cube root of x. What makes an origin symmetry is that if you take any point on the graph and you connect that point to the origin via a straight line, you continue that line the same distance in the opposite direction, and you should hit another point that's going to be on the graph. So what this would say is that if you have the order pair x, comma, f of x, then this other point, which is right here, which is located at negative x of f of negative x, this value here, this height, is the same height as this one, but with the sign reversed. And what that would mean is that this would be equivalent to the negative of f of positive x. But that's what a origin symmetry would look like. In the next part, we want to find the zeros of the function algebraically. So to find the zero of a function, we're looking for where we get an output equal to 0. So to do this, you simply set the function equal to 0, and then you solve for the variable x. In 11 part A, let's do that. We're going to take 2x squared minus 7x minus 30. Set it equal to 0. This is a quadratic equation now. You can try to factor it, or if you're not able to factor it, use the quadratic formula. Let's see if this thing factors. We have 2x and x. Factors of 30 would be 1 and 30, 2 and 15, 3 and 5. And we can make a 7 if we have a 5 here, because we'll have a 2 times 5, which will give us 10. This would be 3. And if the last sign is negative, we need a minus and a plus. I'll let it up to all of you to check this, but this does work. The factorization is 2x plus 3 times x minus 5. Actually, no, it does not work. Excuse me. 3 times 5 is not 30. Blah. Okay, back to the drawing board. So 2 times 15, 3 times 10. 4 does not go into 30. 5 does. 5 goes in 6 times. And now let's see if we can find a combination that's going to work for us here. There is one. If we do the 6 here, we'll have a 2 times 6, which will give us 12. And then a 5 times a 1 will give us 5. And if we have a negative 12 and a positive 5, that will work. So sorry about that, but the correct factorization should be 2x plus 5 times x minus 6. Once we have it factored, we can simply go ahead and set each factor equal to 0 individually. For this one, you would subtract 5 from both sides first, and then divide both sides by 2. So we get 1, 0 is x equals negative 5 halves. For the second one, simply add 6 to both sides, and we get x equals 2 to 6. For part B, we want to set this function equal to 0. We have x plus 3 divided by x squared minus 6 equals to 0. This is an equation that has fractions in it. So what you would want to do is multiply both sides of the equation by the LCD of any denominators that you see. That will allow us to clear the fractions. The x squared minus 6 cancels with the x squared minus 6. So we get x plus 3 equals, on the right-hand side, 0 times anything is 0. And now to solve this one, simply subtract 3 from both sides, and we get the solution x equals negative 3. We have one more. To find the 0 of this function, we take the expression, set it equal to 0. This creates one of our radical equations from earlier in the class. The goal is to isolate the radical, so you would add 1 to both sides. We get 2x equals to 1. The next step is we need to remove the radical, so we're going to square both sides. Right, the inverse of square rooting is squaring. Those cancel out. We are left with 2x equals to 1. And then divide both sides by 2, and we would get x equals to 1/2. So x equals to 1/2. For question 12, we're asked to find the average rate of change. Please remember the formula for this one. So if you have a function f of x, and you want to find its average rate of change over the interval a to b, that average rate of change is f of b minus f of a divided by b minus a. So average rate of change. For this function, we want to find the average rate of change from 3 to 6. So that's going to be f of 6 minus f of 3 divided by 6 minus 3. Again, in the numerator, we have two different function evaluations, f of 6 and f of 3. The denominator is just the difference of the x values. So 6 minus 3, we know it's going to be 3. And then to be helpful, let's do the function evaluation part off to the side. So we need to find these two function values. If we plug 6 into the function, f of 6 is going to be 6 squared minus 2 times 6, which is 36 minus 12, which is 24. So f of 6 is 24. If we do f of 3, that's going to be 3 squared minus 2 times 3. That's going to be 9 minus 6, which is equal to 3. So we go ahead and we plug that in. We're almost there. 24 minus 3 is 21. And then 21 divided by 3 would be 7. So the average rate of change of this function between 3 to 6 is equal to 7. Let's do another one. Let's find the average rate of change of f of x equals the square root of x from 4 to 9. This is going to be f of 9 minus f of 4, all divided by 9 minus 4. Let's come over here off to the side. F of 9, that is the square root of 9, which is 3. F of 4 is equal to the square root of 4, which is 2. So we get 3 minus 2, which is 1 divided by 5, or 1/5. In question 14, we want to determine whether the following functions are even, odd, or neither. The test for this is you replace x with negative x. So everywhere we had an x in the original expression, we swap it out for negative x, and then we try to see what this reduces to. So as a reminder, if f of negative x equals to f of positive x, in other words, if you plug a negative x into the function and you end up getting the same thing as the original expression you started with, then that means that f is even. On the other hand, if you plug negative x into the function and you get the opposite of the original expression, then that would mean that f is odd. And if you get something completely different other than either one of those two, then it would be neither. Okay. So we plugged in negative x for x. We now want to simplify this. This is going to be a negative x cubed plus 6x. And now once you simplify it, you immediately check, is this the same thing that we started with? The answer is no. This is not equal to f of x. So one thing we would know is that the function is not going to be even. If it's not even, then the next step would be to factor out a negative from what you have, and to see if with the negative factored out, did we recover the original? And the answer is yes, we did. If I look at what's in the parentheses, that is the same thing as the function we started with. So what this shows is that f of negative x is equal to the negative of f of x, and that means that the function in A would be odd. Okay? So that function f of x is odd. Let's take a look at g to determine if g is odd or even or neither. Again, we replace x with negative x. Looks like this. Negative x to the fourth is the same thing as positive x to the fourth. This would become a positive 5x. So we plugged in the negative x, we simplified it. This is not the same thing as g of x. So we did not recover the original, so g is not even. If it's not even, the next step is to try to factor out a negative. And then see if you recover the original. With that negative factored out, this is not the same thing as g of x on the inside, so it's not the negative of g of x. So that tells us that g is not odd, and it's going to be neither. So it's neither. We have one more. Let's take a look at h. Everywhere we see an x, we're replacing it with negative x. We simplify this, we get x squared plus 9, and that's exactly equal to the original function. So here we have h of negative x equals h of positive x, and that tells us that h is an even function. So this one is even. In example 15, we now want to graph the function. This is our transformation information. To start, we want to identify what would the parent function be. So here the parent function would be the square root of x. So let's begin by graphing the square root of x, which we should have memorized by now. Couple key points on that graph would be 0, 0, 1, 1, and 4, 2. So the graph of the parent function looks like this. To graph our function, we need to see how it's going to be viewed from that one as a transformation. Notice we have a subtraction by 5 on the inside. That's going to be a horizontal shift 5 units to the right. And we also have an addition of 1 on the outside. That's going to be a vertical shift 1 unit up. So all we need to do is take every point, move it 5 to the right and also up 1. So if I take the point that was at 0, 0, I'm going to move it 5 to the right. So I'm coming over 1, 2, 3, 4, 5, and then up 1. Right here. This point, which is at 1, 1, I go over 1, 2, 3, 4, 5, and then up 1. And then the point that was at 4, 2, I move it over 5. 1, 2, 3, 4, 5, and then up 1. And it's going to look like this. And the graph in blue would be the graph of the square root of x minus 5 plus 1. Couple key points that are going to be on this graph. We have the ordered pair 5, 1. We would also have the point 6, 2. And we have the point 9, 3. Let's take a look at the graph in 16. We want to graph the negative of x minus 3 cubed. So first things first, let's start off by graphing our parent function. This function is going to be derived from the cube function. The graph of x cubed passes through 0, 0, 1, 1, and also 2, 8. We also have negative 1, negative 1, and negative 2, negative 8 like this. So this is our parent graph. This is what the graph of x cubed looks like. There's a couple things that's being done to it. Let's look at the transformations. We have subtraction by 3 on the inside. That's going to be a horizontal shift to the right 3. We also have multiplication on the outside by a negative. That's going to be a reflection with respect to the x-axis. And if it helps, you can do this in steps. For example, I can move everything over 3 first. So let me maybe do this graph in orange. If I move everything over 3 to the right, it's going to look like this. So we have this part. This would represent the graph of x minus 3 cubed. And now once we have this graph, we simply need to reflect it across the x-axis. So every point that's on the x-axis will be a fixed point. Any point that was below, it's going to get moved above. So this point that was at 2, negative 1 is now going to appear at 2, positive 1. The point at 1, negative 8 now gets moved to 1, positive 8. 4, 1 gets moved to 4, negative 1. And 5, 8 gets moved to 5, negative 8. And this would be the graph of the negative of x minus 3 cubed. Again, we want to label 3 points that are on this graph. We have the point 3, comma 0 is there. We have the point 2, comma 1. And we would also, for example, have the point 4, comma negative 1. Let's take a look at the graph in 17. We were asked to graph g of x equals 2 times the absolute value of x minus 1 plus 4. Here our parent function would be the absolute value. Let's go ahead and graph that to begin. Again, it's piecewise linear. Looks like the graph of x between 0 and infinity, and it looks like the graph of negative x from negative infinity to 0. So this is our parent graph. Now we need to see what kind of transformations are being done to this. Notice that we have what? A horizontal shift, 1 to the right. We have a vertical stretch by a factor of 2. And then at the very end, we have a, I should say stretch here. Shift and stretch both start with the S. So vertical stretch by a factor of 2. And then we have a vertical shift up 4 units. So again, if it helps, let's do these in pieces. So let's first shift it over 1. So I'm going to take each point and move it 1 to the right. That would result in this. So we shift it over to 1 to the right. Now we're going to apply the vertical stretch. The vertical stretch is going to take each ordered pair and it's going to multiply the output, the y value, by 2. So for example, I'll do this one, let's say, in maybe purple. If this point was at negative 1, comma 2, now it's going to be at negative 1, comma 4, because 2 times 2 is 4. This point, which was at 0, 1, is now going to be at 0, 2. The point at 1, 0, 0 times anything is still going to be 0, so that stays there. The point that was at 2, 1 now gets moved to 2, 2. And if we have, let's say, that should be good enough. Let's go ahead and draw those. So this would be our graph right now of 2, absolute value of x minus 1. And now the last thing we need to do to get our final answer is we need to take every point and move it up 4 units. So every point you have on this graph, just move it up 4. And then we can go ahead and draw it. So the graph that you see in blue, this would be our final answer, is 2 times the absolute value of x minus 1 plus 4. It was obtained from the parent graph of the absolute value of x by moving everything 1 to the right, stretching it vertically by a factor of 2, and then vertically shifting everything up by a factor of 4 units. Okay, we do want to label some points on this, and every point that you want to label in the absolute value graph will always include the vertex. This vertex is now going to appear at 1, comma 4. A couple other points we would have would be 0, 6. And then we also have a point over here at 2, comma 6. The next thing we come to is our section on the algebra of functions. Given two functions f and g, we want to find f minus g. This is simply going to be f of x minus g of x. That is 3x squared minus 5x minus 10 minus x minus 5. This is equal to, if we simplify it, we have 3x squared minus 5x minus 10 minus x, and then plus 5. And then if we combine some like terms here, we have a 3x squared, negative 5x and negative x make negative 6x, and a negative 10 and a positive 5 would make negative 5. So when we put it together, f minus g is the function 3x squared minus 6x minus 5. The next one, notice this is a filled in circle. That's a multiplication dot. So this is f of x times g of x. So we're going to take 3x squared minus 5x minus 10, and we're going to multiply it to x minus 5. This is going to be a distributive property problem. We take 3x squared times x. That'll give us 3x cubed. 3x squared times negative 5 will be a negative 15x squared. Negative 5x times x is a negative 5x squared. Negative 5x times a negative 5 is a positive 25x. Negative 10 times x is a negative 10x. And a negative 10 times a negative 5 would give us a positive 50. Lastly, we want to simplify this. We have 3x cubed. The two x squared terms will combine to give a negative 20x squared. Positive 25x and negative 10x will make a positive 15x. And then we have our plus 50. So this would be the function f times g. Lastly, for f divided by g of x, this is going to be equal to, just take the function f, which was 3x squared minus 5x minus 10, and divide it by x minus 5. In 19, we now come to function composition. So given two functions f and g, we want to find their composition and simplify. F composed of g of x, by definition, remember this is f of g of x. So the outer function is f, and the inner function, which is our input, is g. So what we're doing here is we're taking the outer function f. F of x looks like this. F of x says take your input, multiply it by 5, and then add 3 to it. Well, what are we plugging into f? Well, we're plugging in g, and g of x is the expression 2x squared minus 1. Once we have it plugged in, we want to simplify this. This would be a 10x squared minus 5 plus 3, which is 10x squared minus 2. So f composed of g of x is 10x squared minus 2. Let's now do the other composition, g composed of f of x. This is by definition g of f of x. So the outer function is going to be g. What does g tell us to do to an input? Well, g of x says take 2x squared and then subtract 1 from it. So it's 2 times input squared minus 1. And the innermost function, the thing that we're plugging in, is f of x. F of x is 5x plus 3. So that's going to look like this. And we now want to go ahead and simplify this. This is going to be 2 times, be very careful here. When you square that binomial, that means to do 5x plus 3 times another 5x plus 3. You have to distribute it out or FOIL it. I'm going to skip that part. I'll let you all do that. But that's going to be 25x squared plus 30x plus 9. Like this. We can now distribute the 2 in. We get a 50x x squared plus 60x plus 18 minus 1. And then from here, we can go ahead and combine like terms. We have 50x squared plus 60x plus 17. We have one more, which is fun. This is f composed with itself. So let's take f of x. So the outer function is f. F of x tells us to take our input, multiply it by 5, and add 3 to it. So 5 times input plus 3. It just so turns out that what we're plugging into this function is itself. So as my input, I also have 5x plus 3. We simplify this. That's going to give us 25x plus 15 plus 3, which is 25x plus 18. 25x plus 18. In 20, we want to find g composed with f of x. This is g of f of x. The function g says you take your input, you divide it by the input plus 1. Our input is the function f, which is the square root of x plus 4. The square root of x plus 4. So that's g of f of x. And then for part b, they want us to compose this function and evaluate it at -3. Well, because we found this function in part a, all we need to do is plug x equals to -3 into that expression. This is the square root of -3 plus 4 divided by the square root of -3 plus 4 plus 1. On the inside of each radical, you're going to have -3 plus 4, which is 1. The square root of 1 is 1, and then 1 plus 1 is 2. So g composed with f of -3 is equal to 1/2. In question 21, we're asked to determine which graphs are those that have inverses. And there was another test that we had. Remember, this was called the horizontal line test. If we look at the graph in part A, there exists a horizontal line that would intersect that graph in more than one point. So we would know that this graph would not be 1-to-1. So it's not 1-to-1, and therefore does not have an inverse. And the reasoning for that would be by the horizontal line test. If we look at the graph in part B, however, every horizontal line will intersect that graph in at most one point, and that means that this graph is 1-to-1. And because it is 1-to-1, it will have an inverse. And the reasoning is, again, by the horizontal line test. In question 22, we're actually asked to find the inverse of a function, and then we want to verify it by doing the compositions. Here, if f of x equals 6x plus 5, remember this is a three-step process. First step, just revert back to the old notation, call f of x equal to y. The second step, we interchange the x and the y variables, so every x becomes a y, every y becomes an x. And then the third step is you now solve for y. To get the y by itself, we would subtract 5 from both sides. We would get 6 minus 5 equals to 6y. Divide both sides by 6. And we would get y equals x minus 5 divided by 6. This expression for y is the inverse function. So f inverse of x is equal to x minus 5 divided by 6. So that's how we find the inverse. To actually verify that we found the correct inverse, what we need to do is we need to check these compositions. If we do s composed with f inverse of x, remember this should equal out to x. My outermost function is f, which looks like 6 times input plus 5, like this. We multiply the 6's and the divide by 6 cancels, so we get negative x minus 5 plus 5. And then the minus 5 and the positive 5 cancel. So that composition gives us x. And if we check the composition in the other direction, f inverse of f of x, we're starting with f inverse, which looks like input minus 5 divided by 6. And we're plugging into it f of x, which is 6x plus 5. Here, the plus 5 and the minus 5 cancel. We get 6x divided by 6. The 6's cancel, and that again gives us x, which proves our inverse.